Hi, welcome to the section on electromagnetic vector potentials. We are already familiar with Maxwell's equations. Now we are going to rewrite the Maxwell's equations in terms of vector potentials. We can write the Maxwell's equation, that is del dot E equal to rho by epsilon 0, del dot B is equal to 0 and del cross E is equal to minus del B by del T, and del cross B is equal to mu 0 times J plus epsilon 0 del E by del T. So, we are going to rewrite all these equations in terms of vector potentials or scalar potentials. So, this equation, that is divergence of B is equal to 0, allows us to write B as the curl of some quantity, and that curl of that quantity we call as vector potential. So, del dot B is equal to 0 means divergence of some quantity is 0. So, we can write that quantity as the curl of something, and curl acts on a vector. That is the reason why this one we call as vector potential. Next, we rewrite this Faraday's law in terms of this potential, or we have to rewrite some expression for E from this expression, that is del cross E is equal to minus del B by del T, that is the original form of Faraday's law. In this we substitute what is the expression for B, that is del cross A. So, del cross E is equal to minus del by del T of del cross A. Now, we take this del cross as common. So, del cross of E plus del A by del T. Here we are taking del as common and cross also common. So, the remaining is del A by del T. So, we have del cross E plus del A by del T is equal to 0. So, here we have the curl of some quantity is 0. That means, whatever be the quantity inside, it has no curling effect or rotational effect. That means, it is pointing in some particular direction. That is the reason why we can write the quantity inside this bracket as the gradient of some quantity, because gradient measures maximum rate of change of some quantity in some particular direction. So, here we can write this quantity as a gradient of some quantity, and gradient always acts on a scalar quantity, because del is a vector operator, it can directly act only on a scalar, then the answer will become a vector. So, E plus del A by del T is equal to minus gradient of V, or we can write E as minus gradient of V minus del A by del T. So, now we have the expressions for E and B, that is B is equal to del cross A in terms of vector potential A and scalar potential V. Now, we just rewrite the remaining two equations in Maxwell's equation, that is Gauss's law and modified Ampere's law in terms of this vector potential and scalar potential. So, first we are taking the Gauss's law and applying the expression for E. So, initial form of Gauss's law is del dot E is equal to rho by epsilon 0. Then instead of E, we substitute the value of E in terms of V and A. So, del dot minus del V minus del A by del T is equal to rho by epsilon 0. Then now we take the dot product with these two quantities. So, del and del both are the same direction. So, we will get del square. Then del dot del A by del T, here del is a vector operator and this is a vector. So, of course, operator acts on the quantity, that is vector, that is we are taking del by del T common into del dot A is equal to minus rho by epsilon 0. We just multiplied the entire equation with negative sign. So, we got the form of Gauss's law in terms of vector potential A and scalar potential V. So, this is the form of Gauss's law in terms of scalar potential and vector potential. Now, we are going to rewrite modified Ampere's law in terms of vector potential and scalar potential. So, the original form of modified Ampere's law is del cross B is equal to mu 0 times J plus epsilon 0 del E by del T. And here we substitute the values of B and E in terms of vector potential and scalar potential. So, we know that B is equal to del cross A and E is equal to minus gradient of V minus del A by del T. So, this becomes del cross instead of B del cross A is equal to mu 0 j, we just expanded mu 0 j plus mu 0 epsilon 0 del by del T of, instead of E just substitute the value of E, that is minus del V minus del A by del T. Then we expanded del cross A using the product rule. So, we will get del of del dot A minus del square A, just we use the result of A cross B cross C. So, del of del dot A minus del square A is equal to mu 0 j, then here mu 0 epsilon 0, this del times del V by del T, that is this is gradient. It can act on a scalar quantity or it can act on a time derivative of a scalar quantity, both are same. So, mu 0 epsilon 0 gradient del V by del T, then next one mu 0 epsilon 0 del by del T of del A by del T, that means del square A by del T square. So, the last term becomes minus mu 0 epsilon 0 del square A by del T square. Now, we just recollect the second order coefficients in one term and first order in the second term. So, here second order, that is with respect to space and this is with respect to time. So, we have taken del square A to the other side. So, del square A minus mu 0 epsilon 0 del square A by del T square, this term. So, it collected into one parenthesis minus del of del dot A, that is this term, then this term also, that is mu 0 epsilon 0 del V by del T. So, del of del dot A plus mu 0 epsilon 0 del V by del T is equal to the remaining quantity, that is mu 0 j minus mu 0 j. Here we have taken this quantity to the right side and mu 0 j to the left side, then we collected second order derivative as common, then first order derivative in the another section. So, here we can see that when we rewrite the Maxwell's equations in terms of vector potential and scalar potential, we may feel that it is looking much complicated, but actually the thing is that whenever we are dealing with Maxwell's equation, we have to find E and B and both are vector quantities. So, each vector quantity is having 3 terms, that is along x, y and z. Similarly, for magnetic field also it is also having 3 coefficients Bx, By and Bz. But when we deal with the vector potentials, we have rewritten E in terms of V and A and B in terms of A. A is vector potential, so it is having 3 components, but V is scalar vector potential, that means it is having only one component. That means we have reduced the problem of finding 6 coefficients to 4. So, that is the advantage of writing the Maxwell's equations in terms of vector potential. We can reduce the number of components from 6 to 4. That is much advantageous, because if you find A and B, we can easily find B and E, because B is del cross A and E is minus del V minus del A by del T. So, the advantage of potential formulation is that even though the Gauss's law and modified Ampere's law looks much complicated, but actually it reduces the problem from finding 6 components to 4 components. Next, we are going to discuss about gauge transformations. So, we have seen that we can write B as del cross A and we can write E as minus del V minus del A by del T. So, we have expressed B and E in terms of V and A. Now, we are checking whether we have any freedom to add some quantities to A or V in such a way that it does not change the original fields, that is E and B. So, for that we are checking, we are taking 2 sets of A and 2 sets of V, such that the new set of A is denoted as A dash, that is equal to A plus alpha, and new V is denoted as V dash, that is equal to V plus beta, and we are adding some quantity to V and A in such a way that it will not change the original electric and magnetic fields. So, that is a restriction. We can add something to A and B, but it will not change the original quantities. So, initially we have the expression that is B is equal to del cross A, and now we choose one more set of potential, that is A dash, that is equal to A plus alpha, but we should get the same answer for A and A dash, because B is equal to del cross A. So, now we can check whether we are getting the same answer in which condition. So, instead of A, I am substituting A dash. So, del cross A dash is equal to del cross A plus del cross alpha, because my new A dash is A plus alpha. So, del cross of A dash means del cross of A plus del cross of alpha, but I should get the same answer, that is B itself. That means del cross of A dash should be del cross of A, which implies that del cross of alpha should be 0. That is, del cross of alpha is equal to 0 means, how can I write alpha? Because curl of some quantity is 0, that means that quantity I can write as the gradient of some scalar quantity. So, I have written alpha as the gradient of some scalar quantity. Here I have chosen the scalar quantity as lambda. So, instead of alpha, I got the value that is equal to gradient of lambda. Here lambda is some scalar quantity. So, we can add a quantity del lambda to A, then the new A dash will not change the original magnetic field. So, that is the gauge degrees of freedom or gauge transformation. We have the freedom to add some quantity to vector potential in such a way that the quantity we have added does not make any change to the original magnetic field. So, here we have added del lambda, here lambda is some scalar quantity. Next, we can check, we have chosen two sets of V also, V and V dash, and V dash is such that V plus beta, and here also we can use the same logic, that is E is equal to minus gradient of V minus del A by del T, and my new V dash is, so I am checking for new V dash. So, I should get the same answer. So, minus del V dash minus del A dash by del T. So, for both V dash and A dash also I should get the same electric field. In that way only I can add some quantity to V or A. So, del V dash minus del A dash by del T, but V dash is V plus beta, that is this expression becomes minus del V minus del beta minus del A dash by del T, means it contains del A by del T, then A dash is A plus alpha, or I can write, that is we have already seen that alpha is nothing but del lambda. So, del A by del T, that is A dash is A plus del lambda, this is not dash, the original A dash is A plus alpha, or A plus, instead of alpha I can write the value del lambda. So, del A dash by del T means del A by del T plus del by del T of del lambda. So, this one and this expression should be same, that is minus gradient of V minus del A by del T is the original expression. Now, I modified my V and A with the new set of V and A, that is V dash and A dash. Then I got this expression, that is minus gradient of V minus gradient of beta minus del A by del T plus del by del T of gradient of lambda. So, if these two expressions are equal, means that this quantity, that is del beta and this quantity should be 0, because the remaining quantities are same in these two expressions. So, only difference is minus del beta and plus del by del T of del lambda, or we can write the gradient of, because gradient is common here, gradient of beta plus del lambda by del T should be equal to 0, because both the terms are negative. So, we can take it as common. So, gradient of beta plus del lambda by del T is equal to 0. So, from this expression it is clear that the quantity inside that is beta plus del lambda by del t is independent of position, that because del is a vector differential operator and it depends on position. So, when vector differential operator acts on a quantity, we are getting the answer as 0. That means, the quantity inside the bracket is independent of position. So, we label it as k of t. So, beta plus del lambda by del t, we label it as k of t. So, we will get beta as minus del lambda by del t plus k of t. So, from here it is clear that beta is a function of minus del lambda by del t plus k of t, and now we define our lambda in such a way that it contains k of t also. So, initially we have some lambda and now we modify our lambda in such a way that it contains this k of t also, because from this expression it is clear that lambda depends on time, otherwise it will become 0. So, we modify lambda in such a way that it contains k of t also. So, we are rewriting this beta as beta is equal to minus del lambda by del t itself. I told you that this I have included this k of t inside the lambda, and that lambda is this one. So, beta is equal to minus del lambda by del t. So, we got the expression. Initially our a dash is a plus alpha. So, we find the value of alpha and we have seen that is equal to del lambda, and initially v dash is equal to v plus beta, and just now we have find the value of beta, that is equal to del lambda by del t. That means, a dash is equal to a plus gradient of lambda and v dash is equal to v minus del by del t of lambda. It will give the same E and B. So, this is gauge transformation. That means, we are changing A and V in such a way that we are adding gradient of a scalar quantity to A and we are subtracting del by del t of the same scalar quantity from V. Then the original electric field and magnetic field remains unchanged. So, this degrees of freedom is known as gauge degrees of freedom. That means, we can change scalar potential and vector potential to such a value such that E and B will not change. That is our freedom. We can change it, but it will not change our original quantities. So, we have seen that if we add these quantities, it will not change the original electric and magnetic field. Okay. Next, we are going to discuss about Coulomb gauge. So, we have seen that the expressions of Gauss's law and modified Ampere's law in terms of scalar potential and vector potential. So, this is the expression of Gauss's law in terms of scalar potential and vector potential, that is del square V plus del by del t of del dot A is equal to minus rho by epsilon 0. In order to simplify this expression, we are choosing del dot A is equal to 0. So, in Lorentz gauge, in Coulomb gauge, we are picking del dot A equal to 0. So, when we pick del dot A equal to 0, the Gauss's law in terms of potential becomes del square V is equal to minus rho by epsilon 0, because we choose del dot A equal to 0. That is Poisson's equation, del square V is equal to minus rho by epsilon 0. Next, we are checking what is the effect of Coulomb gauge in the case of modified Ampere's law. So, this is the expression for modified Ampere's law in terms of vector potential and scalar potential, and here also we are choosing the same thing, that is del dot A equal to 0. That means, this quantity becomes 0. The remaining quantity is del square A minus mu 0 epsilon 0 del square A by del t square is equal to minus mu 0 j is here and we are taking this term to the right. So, it becomes positive, that is mu 0 epsilon 0 del of del V by del t. So, we can see that in the case of Coulomb gauge, we have chosen del dot A equal to 0, but Coulomb gauge does not treat V and A equally. That is, the expression for the differential equation for V and the expression for differential equation for A, both are looking in different way. Next, we can see Lorentz gauge. So, in Lorentz gauge we have the freedom to choose del dot A is equal to minus mu 0 epsilon 0 del V by del T. So, in that case Gauss's law becomes, because this is the form of Gauss's law in terms of V and A. So, here we have chosen del dot A as minus mu 0 epsilon 0 del V by del T, that is del square V plus del by del T of, instead of del dot A I choose this is as minus mu 0 epsilon 0 del V by del T is equal to minus rho by epsilon 0. So, this is del by del T of del V by del T means del square V by del T square. So, del square V minus mu 0 epsilon 0 del square V by del T square is equal to minus rho by epsilon 0. That is a form of Gauss's law in Lorentz gauge. So, here we can see that this is the second order differential equation and it is acting on the scalar potential V. Now, we can see what is the form of modified Ampere's law in Lorentz gauge. This is the original form of modified Ampere's law in terms of scalar potential and vector potential, that is del square A minus mu 0 epsilon 0 del square A by del T square minus gradient of del dot A plus mu 0 epsilon 0 del V by del T is equal to minus mu 0 j, and here we choose as del dot A is equal to minus mu 0 epsilon 0 del V by del T. That is, in Lorentz gauge we pick del dot A as this value. So, del dot A is equal to minus mu 0 epsilon 0 del V by del T means this term goes to 0. So, the remaining is del square A minus mu 0 epsilon 0 del square A by del T square, that is equal to mu 0 j. Then now we rewrite these equations in terms of dealumbation. Dealumbation is denoted as square box square, that is equal to del square minus mu 0 epsilon 0 del square by del T square. So, the original equation for A, that is del square minus mu 0 epsilon 0 del square by del T square of A becomes box square acting on A is equal to minus mu 0 j, or dealumbation acting on A is equal to minus mu 0 j. Similarly, the differential equation for V becomes dealumbation acting on V is equal to minus rho by epsilon 0. So, we can see the main difference between Coulomb gauge and Lorentz gauge. In Coulomb gauge we pick del dot A equal to 0, and in Lorentz gauge we pick del dot A is equal to minus mu 0 epsilon 0 del V by del T. Then here we can see that these are the equations of V and A in Coulomb gauge, and these are the equations for V and A in Lorentz gauge. So, here we can say that the expression for V and A are in different form, but here we can see that the left side is exactly same instead of what is acting on. Here del square acts on V, here del square acts on A, here mu 0 epsilon 0 del square by del T square acts on B, here it is A, and the right side also the corresponding source term is here, because we know that rho is the source of potential. Similarly, j is the source of vector potential, that is del square A minus mu 0 epsilon 0 del square A by del T square is equal to minus mu 0 j. So, the advantage of Lorentz gauge is that it treats V and A on equal footing, and here we can see that both these equations are non-homogeneous equations, and the right side there is the source and the left side the effect of the source. So, now we have seen in Lorentz gauge the equation for V and A, that is del square V minus mu 0 epsilon 0 del square V by del T square is equal to minus rho by epsilon 0, and del square A minus mu 0 epsilon 0 del square A by del T square is equal to minus mu 0 j. And we know the velocity of electromagnetic wave is given by C equal to 1 by square root of mu 0 epsilon 0, or we can say that C square is equal to 1 by mu 0 epsilon 0. So, here we can rewrite this mu 0 epsilon 0 in terms of C square. So, mu 0 epsilon 0 is 1 by C square. So, we rewritten this expression in terms of speed of light, that is C, del square V minus 1 by c square del square V by del t square is equal to minus rho by epsilon 0, and this is del square A minus 1 by c square del square A by del t square is equal to minus mu 0 j, and both these expressions becomes the corresponding Poisson equation, that is this equation becomes Poisson's equation in the case of static, because we know that in the case of static charge distribution V is independent of time and it depends only on position. So, del square V by del t square becomes 0. So, the remaining quantity becomes del square V is equal to minus rho by epsilon 0, that is Poisson's equation. So, but in non-static case or time dependent fields, this is not 0 and we have these expressions. Now, we have to check or we have to find the solutions of this equation. So, from this equation it is clear that the solutions are V and A. So, in static case that equation reduces to del square V is equal to minus rho by epsilon 0, because del square V by del t square becomes 0, and we know the solution, that is V of r. So, here this is static case, that is the reason why potential is a function of position alone, that is equal to 1 by 4 pi epsilon 0 integral rho of r dash d tau divided by r double dash. Here we have chosen a charge distribution in such a way that we have the origin, and from origin to some position, suppose r dash, we have some charges, and from r dash to r double dash we are taking the point, and at that point we are evaluating the field. So, this is the origin. With respect to origin, the position of the charge, that is rho, is a function of r dash. The position of the charge is measured with respect to origin and it is at a distance r dash. Then from the charge distribution we choose a point P which is at a distance r double dash from the charge distribution, or we can say that the point at which we are evaluating the field or potential is at a distance r from origin. So, r dash plus r double dash is equal to r, and here we are evaluating the field at the point P which is at a distance r from the origin. That is the reason why V of r, that is equal to 1 by 4 pi epsilon 0 integral rho of the position of rho, that is we have already said rho is at a distance r dash from the origin, that is the reason why rho of r dash divided by the distance from the charge distribution to the point at which we are evaluating, that is the reason why r double dash d tau. Similarly, in the case of static equation, the differential equation for A becomes del square A equal to mu 0 j, because the del square A by del t square goes to 0. A is independent of time in the case of static case. So, solution is given by A is equal to mu 0 by 4 pi integral j of r dash divided by r double dash d tau. This is exactly same as this one. The only difference is that instead of rho of r dash, here we have considered j of r dash. So, now we have to discuss the solution of that equation, that is del square A minus 1 by c square del square A by del t square is equal to minus mu 0 j, and del square V minus 1 by c square del square V by del t square is equal to minus rho by epsilon 0. These are the original equations. So, now we have to calculate or we have to find the solutions of A and B for non-steady currents. So, what should be the change? We know that if we have a charge distribution at this point, so this is the origin, and from origin we are choosing a charge distribution at this point, is at a distance r dash. From the charge distribution we are evaluating the field at a point which is at a distance r dash from the charge distribution, that is this is the origin. From origin at a distance r dash we are choosing a charge distribution, then we are evaluating the effect or that is potential at the point P which is at a distance r double dash from the charge distribution, and the point P is at a distance r from the origin. So, here there is some charge distribution and we are measuring the effect of that charge at the point P which is at a distance r double dash from the point at which there is charge. So, to travel this much distance, that is r double dash, the charges are moving or electromagnetic effect is spreading, and we know the speed with which electromagnetic waves are traveling, that is c. So, to cover this much distance, it takes a time t is equal to r double dash divided by c. That means, if a charge is here, its effects reaches the point P only after time t is equal to r double dash divided by c. So, suppose we are evaluating the effect of charge distribution at the point P, we are getting the effect of charge at the position r dash, but at a time r double dash by c later. We are writing the potential at the point r and at the time t is equal to 1 by 4 pi epsilon 0 the charge distribution at the position r dash, but at a time t r, that is t minus, t is the present time, t minus r double dash by c means an earlier time. So, rho of r dash t r, and this time is known as retarded time. That means, we have some cause at this moment, then it is producing some effect after some time only, or the effect at this moment is due to a cause happen at an earlier time. So, here we are measuring the effect at present time, that is the reason why the cause has happened at earlier time, and here we measure the charge, we measure the potential at the point P at the position r or at the time t, that is due to a charge distribution which is at the position r dash, but that charge distribution happened at an earlier time, that is equal to t minus r double dash divided by c, and that time is denoted as t r, that is known as retarded time. So, V of r t is equal to 1 by 4 pi epsilon 0 rho of r dash t r divided by r double dash, that is the distance between these charge distribution, r double dash d tau. Similarly, A of r t is equal to mu 0 by 4 pi integral j of r dash t r divided by r double dash d tau. So, these potentials depends on retarded time, that is the reason why these potentials are known as retarded potentials. So, we are measuring the effect of charge distribution or current distribution at the position P at the time t, but that is produced by a charge distribution or current distribution at an earlier time, that is t r, that is equal to t minus r dash divided by c. We know that always cause follows the effect, that is the same thing here also happens. The cause is here and we are measuring the effect at the point P, but to reach the cause at the point P, it takes some time, that is r double dash divided by c. So, let me conclude with this. So, we have discussed electromagnetic vector potentials, and we have seen that we can rewrite E and B in terms of vector potentials and scalar potentials. The advantage of writing Maxwell's equation in terms of scalar potential and vector potential is that we are able to reduce the number of components to evaluate. Then we have seen that how to find the solution of this differential equation for A and V, and the solutions are given by V of r t and A of r t for non-steady currents. Then here we have seen that the solutions depends on the retarded time, that is the reason why these potentials are known as retarded potentials. So, these solutions are valid for non-steady currents or for time dependent fields or time dependent charge or time dependent current. The reference textbook for this session is Introduction to Electrodynamics by David J. Griffith. Hope that you had a good time with me. See you on next time. Have a nice day.